Yeah, hello. I'm John. I'm a PhD researcher here at Birmingham, and I focus on the many worlds interpretation of quantum mechanics. And this presentation is going to be focused on a particular concern with the many worlds, which is branch counting, specifically a newer introduced version of branch counting, introduced quite recently by Simon Saunders, which I found very exciting. But then upon reading, felt like I'd hit a few things that needed to be explained. How do I do next? Go back to the slide. There we go. So this is an outline of how the talk will go. Let me just check the time now. So it's just gone 8 minutes past. So I'm going to start off by providing a brief reminder of the many worlds interpretation, very brief, because I'm sure a lot of people here are familiar with it. And then I'm going to recap some of the probabilities, some of the problems with probabilities and branch counting in the many worlds interpretation. Then I'm going to introduce Saunders' new branch counting idea for the many worlds interpretation. And then I'm going to examine the nature of this new rule, the new branch counting rule, and the branches it introduces in detail. And then I'm going to present a series of worries concerning their usefulness in helping us with the probability problems in the many worlds interpretation. And then I'm going to suggest possible future directions, because I really like this idea of Saunders, but I don't think, I think there is a direction where it could have legs, as it were. So hopefully conclusions to be reached. Look away if you don't like spoilers. Is Saunders counting branches? I'm going to say effectively no, if you take branches understood as a traditional branch counter would. Does counting these things help branch counters anyway? I'm going to say no, they don't. Does this branch counting help the many worlds interpretation in general with probability? I'm also going to say no, but are there potential way forwards? Yes. So to begin, I'm going to start with a brief recap of the many worlds interpretation. Here, once the mouse is visible, good. So to introduce this, let's consider just an arbitrary quantum system, where we know the outcome of measuring this system seems to us to be probabilistic. We know it's at a superposition, and we know that when we measure it, there is a probability distribution over the possible outcomes we could get. If we wanted to find the probability of it appearing in one of these states upon measurement, we'd use the Born rule, which says we project the system onto the state that we're interested in and find the mod squared of that. So we have a system, and this is the bare bones of quantum mechanics rather than just the bare bones of many worlds. We have a system, we can project it onto a state, and we find the mod squared of that, and that tells us the probability of finding that system in that state. However, if we measured the system again, we would find it as if it had just evolved from the state we found it in the first time. At this point, it would appear to us as if the system had actually become its projection. That it has actually done this, and not just in appearance to the observer, is referred to as the projection postulate. Now, in Everett and then the many worlds, we reject the projection postulate, and instead of saying, loosely put, that the system leaves its superposition to become one of its states, instead we say that the observer joins the superposition, and there's an observer that sees each of its states, as it were. So before a measurement or experiment, we have a system where the observer and its environment can be factored out, and then afterwards we have a system where there's an observer that sees up and an environment entangled with that observer, and there's an observer that sees down and an environment entangled with that observer. So at the very basic level, these are the branches or the worlds of Everettianism. So put it graphically, we have Alice before the experiment at T1. She performs an experiment at T2, and at that point, branches up and down, such that there is an Alice that sees outcome up, if it was a spin experiment, say going spin up or spin down, and there's an Alice that sees outcome down. And we could use, well, we could stipulate what the Born rule would have told us here, as a likely probability distribution it could give us, with the probability of seeing it up being a third, and the probability of seeing it down being 2/3, notably uneven. So even though this is not the problem I'm focusing on in the talk, it's so intertwined that I'm going to mention this briefly at the start. So this is like the fundamental problem when thinking about Everett and probability to begin with, is the idea, is what's referred to as the incoherence problem, which is if everything happens, then where does uncertainty or probability come from? So one might think throwing a die, part of the fact that the outcome is uncertain is that you'll only get one result. You won't get all 6 sides come up, but if you threw the die and it unfolded to reveal all of its sides, you've got all of the results, you might be wondering where probability or uncertainty could fit in. So if we go back to here, we can see now we're getting all of the results rather than just one. So the question would be, where does probability come in at all? And there are 2 answers to this I'm going to quickly go over. There's a subjective uncertainty reply, which says that that subjective uncertainty can enter the, so I'm just checking my notes on a different machine. Yeah, subjective uncertainty can enter at 2 possible stages, before and after the experiment. After the experiment, it could be the case, and this is how it's cashed out sometimes, that we have Alice has branched, she's in her up world and she's in her down world, but she has yet to look at her experiment, and she has yet to look at the measuring device. She doesn't know which world she's in. So she could have subjective uncertainty at that point over which world she's in, and that's the kind of thing you could assign a probability distribution over. There's also before the experiment, if you were doing a diverging picture of branching rather than an overlap one, then what you could say, in which case there's an even number of Alices before and after the experiment, and the Alices, instead of kind of splitting or becoming duplicates, partition such that some of them will see up and some of them will see down. So at that point, we could say that before the experiment, the Alices are could be uncertain of which history they're in, or sorry, which is their, what's in their personal future, or which Alice they are. Another reply that's often given is the decision theoretic approach, introduced by Deutsch and championed by Wallace. Let me just check I'm getting this one right, which is where probability is just whatever fits the role of probability in decision theory, essentially, boiling it down. So a functional definition of probability, and they argue from the principles of rationality and after accepting the Everettian picture that the mod squared amplitude fits this role. So they're arguing that that as the mod squared amplitude fits this functional role, our probability in our decision theoretic schemas, then we should accept it as probability. It's 2 potential replies to the incoherence problem. But the problem I'm focusing on today is, next slide, the problem with original branch counting. So I'm calling it the original branch counting rule because Saunders has introduced a new branch counting rule, a new idea of branch counting that I'll present later after these slides. But the original branch counting rule, the worry is that it's not, that there is something that is dictating our probability ascriptions, but it is not the Born rule. It is something that disagrees with the Born rule. So an original branch counter might think something along the lines of, would think something along the lines of, how you determine the probability of seeing a specific outcome is the number of branches with an outcome divided by the number of branches in total. So here, in a very simple toy example, we have Alice. She sees up and she sees down. How many Alices see up? That's 1. So 1 over 2 is a half. So grab my water. And then how many Alices see down? That's also a half. And this would disagree with the Born rule. As we said, we've got the Born rule here saying that we've got 1/3 for up and 2/3 for down. So we don't want to accept branch counting. So if you're somebody assessing the many worlds of the Everettian interpretation, for whether you want to accept it or not, but you're also a branch counter, you might start to worry that you couldn't accept Everettianism at that point. And it could be quite intuitive branch counting, but I wanted to quickly present some more substantial motivations for it, just to highlight why it should be a worry. So this is an argument here given by Disargi Barmani in 2013. He argues that the branch descendants are identical evolutions of the agent in respect to personal identity. So over here, whatever grounds personal identity over over time, sorry, he wants to say is symmetric for the up Alice as it is for the down Alice. So whatever grounds personal identity over time is identical for each descendant. We could take things like amplitude as irrelevant to personal identity over time, but it doesn't matter the amplitude of the branch Alice is on, that they will stand in the same personal identity relation, the thing that preserves personal identity over time. He then notes it would be irrational to think that one evolution is more likely than another when the evolutions are all equally the same person, and that would be if we're accepting probability entering Everett through subjective uncertainty. And he notes that it would be irrational to care about one evolution more than another when the evolutions are all the same person, which he thinks would be the consequence of the decision theoretic approach to introducing probability into Everett. So it's a more substantial motivation to the original branch counting thought. The concern then is proportion of observers. So let's look at Saunders' new branch counting rule. Let me just have a look at my notes. So will Saunders' new branch counting rule help us with any of these problems? Will it help us overcome the worry that the branch counters would have about the concern about the number of observers? And will it help us with something like the incoherence problem or how far probability enters Everett anyway? So to do this, I'm going to have to briefly introduce the consistent histories approach to the many worlds. So we start off with what would be a series of parameter spaces. And this is important for Saunders later on. So we'd have three parameter spaces, which would each be a space of the complete ways things could be at a specific time. Regions of these parameter spaces would be coarse-grained ways things could be. For example, seeing up or seeing down without worrying about how many subatomic particles you've been bombarded with, something like that. So things coarse-grained out. So we would have, for instance, A could be seeing up or B could be seeing down. And then we're going to make the quantum move. We've got an initial state of the world here, or state of the universe, and we're going to go associated with each parameter space is a set of exhaustive, commuted Heisenberg picture projectors that project one-to-one the initial system, or the systems inherited from the last projection, onto the unit vector associated with the parameter region representing those outcomes. So what that means is you've got the original state here, and you'd have a projector that evolves the state, more like a right angle actually, but evolves the state to this time and then projects it onto the region, projects it onto the unit vector in the Hilbert space associated with the outcome with a certain region of parameter space. And then it does it again with another projector, and then it does it again. And then what we have is a chain operator, which is doing this evolve and project, evolve and project, evolve and project. And this would represent like a certain history, a way things could be. These time index strings of projectors would be a history. And then we have to introduce, level of grain. We can start by looking at the projectors themselves before we look at the histories. So we're going to let projector alpha, projector beta be two arbitrary non-zero projectors on Hilbert space. Then we're saying that one is coarser grains than another. If it is the case that there is an exists a projector that you could add to beta that isn't beta or alpha that produces alpha. The idea would be then that the more coarse-grained one would represent a region that encompasses but is not equal to the finer-grained one in parameter space. And then we could talk about one history being finer grains than another. If for each member of its sequence, where their time indexed and matched up, that the projector, the finer-grained one, is finer-grained than its counterpart in the coarser-grained one. We can now introduce the property of it being consistent, the constraint. So we could say for any history in this space, the spaces we're considering, it is a decoherent history and then consistent if for any other history that's in that space that is non-identical and incompatible. And what I mean by incompatible is they don't stand in the coarse grading, fine grading relation to one another. That if you evolve the first state with one and you involve the first state with the other, you'd get approximately zero in the product. There'd be very little overlap between them, approximately none. So now we've introduced consistent histories, you can introduce Saunders' idea about how to count new branches. Now, the upshot is 5. The upshot is this one here, is that we're going to end up with the amplitude of a history that would have previously represented an outcome. So, for instance, we had these O's, consider these O's to be chain operators, history operators, that are representing things we'd have thought to be outcomes before, like seeing up at the end of a chain or seeing down at the end of a chain. And what we're going to get is we're going to get a proportion, to be proportional between the amplitude that would be returned, the associated amplitude, I'm going to call it, when that projector is applied to the initial state, and the cardinality of the decomposition of that projector, plus some rounding error, because how we're going to get to that is via dividing by tau, which I'll go into just now, but it's going to leave us with a little bit of a rounding error, and that will come out as an error in the end, such that the smaller the tau, the smaller the error. So just to quickly go over what's going on here, we start off with the idea of a history space that's maximally fine-grained histories, and we consider a subspace of that D that contains all of the histories whose associated amplitude is tau, which is a hopefully very, very small value that we've picked, such that we could go as small as possible before we start to lose decoherence on our space. What we do then is we get the history operator that would have represented an outcome, and we decompose it into a set of tau operators that are all finer grained versions of it. It would then, yes, so that's what's being said there, that we decompose it, then the sum of them would return the outcome operator, but then also, as we could sum the associated amplitudes for the decomposition, we can get the sum of the taus in the decomposition set to equal the amplitude of the outcome operator. Then, if we divide the left side by tau, we get, hang on, let's make sure I'm saying this properly. So what we can say is that when we divide the amplitude by tau, given some remainder, we'll get the cardinality of the decomposition. So we've got the cardinality of the decomposition is proportional in some way to the amplitude that would be associated with the outcome. Then we square both sides, so we can get the quantum probability on the left, or we could do it with a subspace here such that tau drops out. But not to linger on the proof too long. The upshot is now we've got an outcome history, or what would have previously been an outcome history. Let's go back to. So we would have had a history that would represent, say, Alice seeing up here, and a history of Alice seeing down. And instead, now what we're doing is we're fine-graining those histories such that they're now composed of equal amplitude histories, such that the cardinality of each of these histories is proportional to the returned amplitude when you apply that operator, that history operator. Let's go have a drink. So just to give a really toy example. So previously we would have had 2 history operators, one that represented up and one that represented down. We then introduce an imagined background quantum system in a single position of 2 states, evenly weighted. We keep the up history coarse-grained so that the decohered state could be in either state. This new system then would be coarse-graining out the states of the decohered state. But then we'd fine-grain the down history so that we got 2 operators. And then we get the correct proportion. A big toy example, because we wouldn't want tau to be that large usually. I think I'm missing a slide. Really? Oh no, it comes up later. So the question that occurred to me at this point, and the worry I have here, is that are the things we can, are these histories, are these tau histories, are these histories that are outcome histories are decomposed into, are they what you would call branches? Are they branches? I'm going to say if you're like one of the traditional branch counters, like I mentioned at the start, and not one of Saunders types, as it were, then branch counters seem to be concerned with whatever it is that is in one-to-one correspondence with observers and proportions of these. And that doesn't seem, immediately we can see that doesn't seem to line up well with the notion of the tau history. So the question becomes, can Saunders branches tell us about observer one-to-one branches, importantly, the ratio of observers to outcomes? I'm going to say its branch characters seem to be more concerned with histories that are fine-grained up to decoherence, or at least that are in some way one-to-one with observers, and that we can know this, and note that a tau history could pick out lots of decohered worlds, fine-grained at the loss of decoherence. Oh, I've gone the wrong way. So just to illustrate this, let's use this example. We've got Alice performs experiment 1 on a quantum system with 2 distinct outcomes. Outcome 1A and outcome 1B. She then performs a second identical experiment with outcomes 2A and outcomes 2B. And we say history 1 does not look like the type of thing that a branch counter would be interested in. If we're accepting Everett, there'd be at least 4 Alices in this one history, because she would have branched from experiment 1 and branched from experiment 2 at least. However, history 1 is just one history, and it's one history that could encompass a whole number of Alices without a constraint of proportion. This would mean that it does not tell us much, does not tell much to the branch counters who are concerned with observer ratio. History 2 is more what the original branch counters are interested in. Specifically, if we specify that there was no one accounted for Alice, there's just one Alice per this history. So for all superimposed entanglements, a state was specified. In this sense, we have fine-grained up to decoherence, a loss of decoherence, sorry. So it seems at this point that as there's no constraint how many number of Alices are in a tau history, and history 1 could be a fine tau history, then it doesn't seem like they are branches in the traditional sense. So what we've got here is a more realistic example. We've got Alice, and she's going through, she's evolving before the experiment. She becomes continuously entangled with the environment, such that there are a series of Alices. We could fine-grain histories in accordance with the entanglement from the environment to pick out these Alices. The Alices then perform the experiment, branch up or branch down, and there is no constraint on the number of Alices for up and for down. It would be fine if there were these Alices were approximately proportioned, but we have no guarantee of such a ratio. The only constraint is that there is enough branches to fine and coarse grain to create the tau histories in the first place. So the old branch counter doesn't seem to be satisfied by this. So can we count these tau histories and treat them like branches? So while Saunders branches are something, they don't seem to be the type of thing that the old branch counters would be interested in, and they don't tell us anything about those. But can they help anyway? I'll just scroll down my notes. So putting branch counters aside, perhaps Saunders' position could help with more general problems in the many worlds interpretation concerning probability. Specifically, can it help with the incoherence problems I mentioned at the start? So before going on, we need to introduce an important aspect that I kind of left out at the start of this, which is that Saunders argues to be against the claim of being ad hoc, that his account of branch counting parallels Boltzmannian microstate counting and stack mech thermo. And as a route that probability can be arrived at in Boltzmannian state counting, and he's saying that his tau history counting is a parallel to this. So can we borrow and how much carries across from the statistical mechanics approach to the coherent history approach? So can we borrow this method from statistical mechanics and make sense of it in Everett? And what will it help us with? So to quickly introduce Boltzmannian microstate counting. So Boltzmann's method involves counting the numbers of microstates energetically available to macrostates and comparing the ratio between them to arrive at an entropy difference. This is achieved by 2 stages of partitioning. Firstly, the n-particle phase space is partitioned into regions which represent different macrostates. And then the macroscopic properties could be realized by an infinite number of different points within those regions. So then that we can get a non-infinite count for each macrostate. Each cell is partitioned into further cells of a uniform volume, and which the volume is determined by the Louville measure. I'm probably saying incorrectly, but it's determined by the metrics given by either the momenta or the position dimensions. We can then count microstates and compare the number of microstates per macrostate if we treat these smaller cells as microstates. Let's scroll on to the next thing. So with Saunders position, we partition the parameter space in accordance with the associated Hilbert space norm given on by a system acted on by a projector. This is potentially disanalogous with Boltzmann's method, as the size of the regions of parameter space is given by something other than the metrics that make up the dimensions of the space, but by something else, which we already think guides us in probability. So instead of the parameter space, say, if you had a parameter of position, you divide the parameter space up into even intervals of position, and then you could construct regions of parameter space doing that via different dimensions. Instead, what we're doing is we're getting regions of the parameter space, their volume size determined by their associated associated amplitude for their associated projector, for their associated history projector. Sorry, not history projector, projectors that make up the history projectors. So in this sense, we're not counting things in a neutral way. And there is no reasons these histories stand out to us other than they give us the right answer. So potentially disanalogous, and this introduces the worry of being ad hoc. The sizes of the regions are being determined by something we already think guides us in probability. I pressed the wrong keyboard. Which brings me to kind of my final worry, which is I kind of looked at this from a Lewisian best systems perspective to see why are we including this counting, essentially. So if we've already got probability through the mod squared of the amplitude, why then do we need to also include the tau history counting, especially if it isn't satisfying what branch counters are interested in? So in light of this, we could also look at Saunders branch counting from a Lewisian perspective. Here, probabilistic laws are taken as true if and only if they feature in the account of reality which maximizes simplicity, strength, and fit. Fit being, given the probabilistic laws of the account, the more likely the actual history of the universe was to occur, the better the fit of the theory. Saunders' account seems to be less simple than just taking the amplitudes that directly inform us about probability. On top of having to know the amplitudes, we have to construct new mathematical objects from the amplitudes and use those to guide our probability ascriptions. So it doesn't seem clear why we should add Saunders branch counting on top of our existing model, where we get probabilities directly from mod squared amplitudes. But I do think there are future directions. So because at the moment, it looks like Saunders branch counting, as it's set up at the moment, does not help traditional branch counters and does not help us anyway. However, all is not lost for what there are possible future directions to go in this. And I was going to include this in the talk, but then I cut it down to 30 minutes, so it's not. But what would be the direction that I'm currently working on for this? I think it's going to have to be something like this. We're going to have to say, the Everettian is going to have to say they strongly believe that the many worlds is true, and they strongly believe that branch counting constraint. Therefore, they're going to have to use that to imply something about unobserved proportions. A bit along the line of like 1985's Deutsch, where he's saying that we're going to have to say something unobserved about the proportions of observers to get it to work. And I think then we could have something like Saunders' tau histories, but then we kind of might need to move to, rather than saying that the proportion of Alice's is just something that is emergent, that we can directly see from the mathematics of quantum mechanics, we're going to have to say that actually we're specifying something unobserved going on. And then what's the cost of that to the Everettian? I'm not sure yet. It could be too much. So conclusions, is Saunders counting branches? I'm going to say effectively no, if you're interested in the traditional notion of branches that's kind of one-to-one with observers. Does counting these things help branch counters anyway? I'm going to say, well, I said no. And does this branch counting help the many worlds in general with probability? I said no. And are there future potential ways forward? Yes. Thank you all for listening.